onto free damped vibration. So now the situation looks like this, where we include a term for damping. So B is not 0 anymore, but the forcing function is still going to be 0. We're still going to work with free vibration. So the solution to this one, again, we're going to look at it generally with the solution to this homogeneous one using the characteristic equation. So this would turn into mr squared plus br plus k equals 0. And then to solve for r, we'll use the quadratic formula. So we have the opposite of b plus or minus the square root of b squared minus 4mk all over 2m. All right, so there's our solutions for r. And we've talked about this before with homogeneous equations in general, but the type of solution you get really boils down to what this value is here. So the type of solution depends on this. And back when we were discussing second order equations, homogeneous equations to begin with, we talked about those three cases, the three types of solutions. So what we'll do now is kind of go through again and think about what that means for each one of these cases, what that's going to look like in terms of the vibrational response. So the type of solution depends on this discriminant, and so that's going to describe the three different types of solutions. So let's start with the first case where it's negative. So if we make this, or if we assume that this value is negative, again, this is all going to depend on what values of b, m, and k you have. This is what's called the underdamped situation, and we'll see why we use that term in just a second after we write down the solution and draw the graph of it. So if it's underdamped, this negative value of the discriminant is going to lead to complex solutions for r. And it turns out that if you write this in general, this would look like y of t equals c1 e to the alpha t cosine of beta t plus c2 e to the alpha t sine of beta t. And again, this is just the generic solution with complex values of r that we've seen many times to this point. We can also rearrange this in a similar way to what we did with the undamped vibration, where we can, instead of using that, we could say also y of t equals. Now, if you notice, this solution we have right here is basically the one we had for undamped vibration multiplied by e to the alpha t, right? We could factor this out, and the remainder, after we factor it out, would look just like the undamped solution we had earlier. So we can look back at the solution we had there, and this alternate form will just look like the alternate form we had before, multiplied by e to the alpha t. So we'd have something like a e to the alpha t sine of beta t plus phi. Right, so everything's the same as last time, except it's multiplied by this e to the alpha t because that's multiplied here and here. So it's the same principle as before. The a and phi are the same as before. So a is still the square root of c1 squared plus c2 squared, and phi, the tangent of phi, is still equal to c1 over c2. Now, if you think about what this graph is going to look like, we can draw a graph here, and to draw this graph, I think I'm going to go over to Desmos and play around with these coefficients a little bit. So let's say we have here, we can draw the solution. So y equals, let's see, let's use a, then e to the power of I'll have to use different letters here, so I'll use k t, well, I'll use x instead, times the sine of, let's call it bx plus, I'll use p instead of phi. And close parentheses. So there's the solution here, and let's add some sliders here. Now, if we zoom out, you'll see, it's hard to tell here, but let's make k be something relatively small here. Let's make this negative 0.3. Okay, larger than that. Let's do that. And then if we change the value of b, you can kind of see what's happening, that it's essentially compressing this wave. If we change the value of p, it's going to shift it around. So it basically is moving this graph further to the right. But the overall shape of this is basically a sine wave that's decaying over time. So it's a decaying sine wave. Let's see if I can stretch it in such a way that it's clear to see. So you can see that there's this sine motion to it where it's oscillating back and forth, but its amplitude is decreasing as you go. And so it's constantly or continually trending toward the vibration ending. And that's the idea of the damping, is that the friction causes that vibration to slow down, and eventually the oscillations will get to the point where you can't see them anymore. They're small enough and they're essentially zero. So we can include this picture in the notes. And again, basically what you've got is you've got the sine wave, and if you kind of trace along the peaks here, I don't know how well you can see this, but the shape of that path downward, the shape of that decay is the exponential. That's where this a e to the alpha t is coming from. So that's controlling that, the shape of that decaying exponential. So the alpha here, the k that I used in Desmos, is generally negative, and it's decreasing downward like this. Practically speaking, it's not going to increase vibration without some external force. It's going to decrease based on the values of your parameters in the problem. So that's the underdamped situation, where it's damped, but it still oscillates, and it oscillates in this decaying manner. And of course, by changing the parameters, you can change how quickly that decay happens and so on. But in general, that underdamped situation is when you have complex values for R. The other case, or the other two cases, are sort of the opposite, where we're not going to see this oscillation, but we'll think about why that might occur. So let's take the second case, which is where this discriminant is greater than 0. So if it's greater than 0, going back to this quadratic formula, if that's positive, that means that you're going to have two distinct real solutions, right? Because if this is positive, then this plus or minus leads to two answers, and again, if it's positive, it's going to be real solutions. So that's the situation where we have two distinct real solutions. This is the case that's called overdamped. And we'll see why that is, again, when we write down the solution and graph it. If you think about the two distinct real solutions, your graph is going to look like, or your solution is going to look like C1 e to the R1t and C2 e to the R2t. Now it should be noted that R1 and R2 are both negative, again, for a physical real situation. These would both be negative. And then if you draw that graph, these negative exponentials are going to again decay down to nothing very quickly. And so it turns out that this situation, you don't actually see oscillation. So again, if we go over and look at the graph of this, so in this case, we'll have y equals I'm not going to worry about what C1 and C2 look like to begin with. So we'll just have e to the power of, let's call it a x, and then plus e to the power of bx. All right, so as we control these values for r, again, these are negative values. If they're both negative, well, they can be both negative and have the solution look like this, where it essentially starts out at some initial value up here at 2 in this case, and of course the constants C1 and C2 control that initial value, but the shape is more what we're interested in here. So this case where it's overdamped, there wouldn't really be any oscillation. The mass would just immediately move back toward the equilibrium solution without bouncing past it and then coming back and forth and back and forth. And then if you control, I don't know if I can do this well enough to see this. It's hard to get the right values that'll make this work. But it turns out, depending on your values of C1 and C2, so let's say if one of these was negative, let's do that. So in this case, you've got basically the solution starts at 0 and then increases upward and then decays back down. Let's see if I can change these a little bit. So in this case, the solution starts here at 0 for our position, but it starts somewhere else, and it increases upward. So there's an initial condition that's initially forcing it away from the equilibrium, and then once it moves away, then the spring takes over and starts pulling it back, and it quickly again comes back to the equilibrium. And then if we switch these around, it would kind of do the opposite, where it would start initially going the opposite direction and then move backward. So there can be some amount of variation. It doesn't necessarily have to immediately go towards 0, but there's kind of those three cases. So I'll just draw kind of a idealized portrait of each of them. It could look something like this, where we see it starts here and then just immediately trends down towards 0. Or it could start somewhere and then initially go up and then trend towards 0. Or it could even start somewhere here and go down past it and then trend towards 0. So these are kind of the situations, but ultimately it very quickly moves toward the equilibrium solution, even if there's initially some amount of what we would call overshoot, or really this one would be called overshoot here, where it goes past the equilibrium and then comes back. So it doesn't really oscillate in that sense, but it might move past in one direction or the other once and then come straight back. So that's the overdamped situation, where there's so much damping. If you think about it, this value of B is large enough to outweigh the M and the K. That's kind of the idea of the overdamping, is that for larger values of B, you're going to see this situation where it just comes straight back to the equilibrium solution without seeing much vibration back and forth. Then the third case is kind of the middle ground between the two, more or less, where you've got this discriminant equals 0. And if you think back to, again, the introduction to all of this, if that's true, this formula in the quadratic formula, this is all going to equal 0. So all you're going to have for your solution is this negative b over 2m. There's no plus or minus happening if everything after it is 0. So that's the case where you get just one real solution instead of two distinct ones. So you have one real solution, which of course is negative b over 2m. This is what's called the critically damped situation. So in this case, R just equals negative b over 2m, and your solution, y of t, looks like c1 e to the rt plus c2 t e to the rt. Again, a familiar solution. So this one also doesn't actually oscillate. It looks very similar to the overdamped situation. The reason it's called critically damped, though, is that this is the situation where B is as small as it can be without seeing oscillation. So there's kind of this tipping point where if the damping coefficient went any smaller at all, you would start to see oscillation. And the oscillation would kind of start slowly. If you go back here, if B is just small enough to see oscillation, it would start very, very slowly and very quickly trend towards 0. But then as the damping decreases, this wave starts to oscillate longer and longer, and the oscillations last longer until the point where there's no damping and it oscillates infinitely. So the idea of critically damped is that it's right on the edge of oscillation. So it still doesn't really oscillate, but it's as close to it as possible. So it's at the critical point where if B were any smaller, it would. That's the idea of the critically damped. So again, if you look at this, you'd see a graph where, let's say, for instance, it could look something like this, where there's kind of one overshoot, one pass, and then it comes back to the equilibrium solution very quickly. So those are the three possibilities if you have damping. It could be overdamped, underdamped, or critically damped. And really, underdamped is the one that we kind of think of when we think of actual vibration, where it's oscillating back and forth. These other two are maybe less familiar ideas. But you see these kind of things a lot if you deal with vibrations or with controls, which are kind of related, the dynamical systems in general. You see this a lot where the values of these parameters control the type of solution you get and what the overall picture looks like. And by tweaking these parameters, you can see a big difference between the types of solutions that you get.